Right. Now I will give you some values. First value is now we are going to talk about sodium chloride. Right. Delta H naught. I'm trouble with my blackboard. Let's go on like this. Give me a second. I'm going to restart it. Right. Right. This is my question. I'll start off with a very easier one. Right. This is the data. This is for sodium chloride. Delta H naught, lattice enthalpy for sodium chloride solid, right? And I want you to write the equation, right? Enthalpy equation for this. Okay, yeah, yes, right. Okay, this is the data. This is the amount of energy released, right? And other data is um, delta H naught, hydration enthalpy for sodium plus gases. You have to write the equation for this. Delta H naught hydration enthalpy for chloride minus gases. And the other thing is delta H naught using this data. I want you to write a formula using the Hershey cycle, right? I want you to come up with a formula for delta H naught solvation enthalpy for sodium chloride solid. Right? Using this information, I want you to write the formula for delta H naught solvation enthalpy. For this also, I want you to write the enthalpy equation. Right? So, combining all these four information, I want you to complete a Hershey cycle. Right? Let's see. If you can identify what's there, then you are okay. Right? Remember plus minus values, right? We discussed whether some of these enthalpies are always endothermic, some are always exothermic. Some of these enthalpies are yet to be determined. So I want you to come up with a lattice enthalpy. Not the formation. The first one is lattice enthalpy, second one hydration enthalpy of sodium plus, third one is hydration enthalpy for chloride minus ions. Using these three, I want you to come up with a formula for delta H naught solvation. I want you to use a Hershey cycle for that. Let's see. For you to make the formulas, first of all, you will have to write the enthalpy equations for each of these. Then try to come up with a Hershey cycle. Okay. Okay, let me know once you're done, right? Okay, were you able to do it? Manage to do it? Let us check. Right. Oh, AC the cycle, there's a cycle. Huh? If you can remember, right, I'll write the equation for this right now. Let us do it now. What is the lattice enthalpy of sodium? Some of them are wrong, right? Some of them are wrong. Sodium, if you can remember, lattice enthalpy means amount of energy release what? Ions in gaseous forms are forming a, yesterday we discussed, are forming a ionic lattice, right? This is one that. For this one, hydration enthalpy, yesterday we did discuss what? Sodium plus gas into aqueous medium, you are getting sodium plus aqueous. This one, Cl minus gas with aqueous form, you are getting Cl minus aqueous. Solvation enthalpy, sodium chloride, sol. Okay. This one into aqueous medium, you are getting sodium plus aqueous plus Cl minus aqueous. Now I have given you all the equations needed, right? Using this, I want you to complete a cycle for this one, solvation enter. You know what a Hertz cycle means, right? Okay. Yeah, I'm taking on. Right. As per your answer, lattice enthalpy is You must show the distance of the direction of the arrows, right? Okay, first one is okay. Uh, and then so lattice enthalpy is very good. You haven't put the direction of the arrow for the lattice enthalpies, right? Yeah, you must reverse it, right? Usual lattice enthalpy is for the formation of the solid, right? But to complete the reverse cycle, you must what? Change the direction of the arrows. In that case, sodium chloride, solid aqueous. This is the unknown, right? So they will give you values for each of these lattice enthalpies, and they may ask you to find the unknown. It could be any arrow of the or the enthalpy related to any arrow, right? One is missing with the given value, you must be able to find the same like the Hertz's cycles we have done in the ACEs, right? Hydration enthalpy of Na plus. This is delta H naught hydration enthalpy of Cl minus aqueous. This is sodium plus gas, Cl minus plus gas. Now here's the thing. Now this is the lattice enthalpy to this direction. Delta H naught, sodium chloride, lattice enthalpy. Now to complete the Hertz's cycle, you must have what? Change the direction of the arrow, right? So they are. So you must write a formula for this. Can you write me a formula now? Adding these values, write me a formula for delta H naught solvation using the other enthalpy values. Delta H naught solvation for sodium chloride. So write me a formula using this Hertz's cycle. Okay. Yeah, your answer is fine. The only thing you have to remember, you have to very good. It means hydration enthalpy minus lattice enthalpy. So you can actually remember this as an equation, but I don't like the fact that memorizing these, right? Do not memorize this. So this is the equation enthalpy of hydration is equal to what? Reverse or negative lattice enthalpy. Its enthalpy is always positive, right? Negative value of lattice enthalpy plus hydration enthalpy. Okay. Now we are moving to one of my favorite topics, N coffee. Right. Have you heard about anything called N coffee? Never heard the term also. Entropy is one of the most, yes, it can lead us to many things, right? Even to, like, it's kind of like it's kind of the heart of sciences. Entropy is one of the most important fundamentals of heart of sciences. I'll tell you why. I will tell you in brief. Behind entropy, there's a nice story, right? Now remember, okay. Right. So put the value, the topic as entropy. Now remember, now we know there are two types of now. Before the concept of entropy came into existence, I'm talking about before during the time of industrial revolution. During the time of industrial revolution, people were starting to make machines. Why? The human power was not enough to cater to the demand during the industrial revolution. Right? There's a huge expansion. So they started to make machines. The early day machines came up with what? Steam engines, right? They used water and they were heating it into steam. They were using steam engines. So when we are using steam to power a piston, it involves a lot of engineering and physics. Now, when they were trying to tackle this question or the engineering marvel, they had a wall, right? They had an issue with the theory. They realized. Now remember, this is about thermodynamics, thermal energy. They realize there's a missing piece of the puzzle. Some of the theories are missing, yet have not been understood. Scientists have not understood. Because of the reason, they were unable to make a successful machine out of thermodynamics. So they realized before making the machine, we have to find that theory, right? So inside the head of the scientists, they had this question mark. Okay, they were trying to scientists while the engineers were trying to make the designs, engines. Scientists had the role of finding this hidden factor. No one knew. The one of the interesting questions here was now when you look at the exothermic reactions for enthalpy diagram, can you remember? Here the energy, here the reaction coordinate or the time. If we place the reactants here for exothermic reactions, where would you place the products? Above, above or below? Below. Why is that? These products. Energy, not the energy being released. Products are having low energy, right? So therefore, excess energy is released, right? Remember why the reactants are converted into products. If I ask you that question, why the reactants are converted into products? What is the reason for it? Okay, more energy reactants are products. Which one of these are having high energy? Then product. Then why did they become products then? Why reaction happened? Because God prefers so. Why? I'm asking about science. Like why? There must be a reason, right? React. Why? Why it was released? They could have kept it with them. No? Reactants have high energy. Okay, high energy. Products have low energy. Then why they have become product? There must be a reason. Otherwise, it's a change. The chemical got changed from reactant to products. There must be a reason. It could have been a reactant itself without becoming a product. There must be a reason why they have got changed. Right? It's low energy. Right? Remember, it's kind of like I'm connecting to a normal human behavior. You know, there are married people, unmarried people. People are getting married. Why? They think, why? What is the reason? They think it will make them stable, right? Stable future. They are more stable. Just like the reactants are becoming a product. They are getting married, making a bond. So now they are more stable. Before getting married, they have higher energies. After getting married, they are settled. High energy means when you're driving a car faster and when you're driving a car slowly. Which car is having a higher energy? When you're driving a car faster or when you're driving a car slow? Which car is more unstable? Vulnerable of being faster one. So it means high energy means unstable. Very that is the reason. Unstable. High energy means unstable. Low energy means more stable, just like a driving a car. That is why reactants are becoming a product because products are having low energy, so they want to become stable. That's a general principle. That is okay. Ah, scientists understood. It makes sense. So these type of reactions are spontaneous. Why? Everybody likes to become stable. So therefore, no question about it. Right? These reactions are spontaneously happening. Delta H naught minus. This was okay to be understood. But they realized when it comes to what? Endothermic reactions, even some endothermic reactions are also happening spontaneously. So in that case, reactants are becoming products. So what becomes? It means products are having high energy, they are becoming unstable, less stable and unstable. Even though products are becoming unstable, still the reaction is happening spontaneously. Now they are also giving question mark. Now by looking at the enthalpy, if the enthalpy is what? Negative, if the reaction is exothermic, it is okay, reaction is happening, it is feasible reaction. Reaction is happening, feasibility is there, thermodynamically feasible, right? Thermodynamically feasible. Energy wise, it is feasible. Why? Products are having low energy, feasible reaction, right? Because it's an exothermic reaction. But still, endothermic reactions are also happening spontaneously. Very good. No, that is the case, but they were not able to explain that. They were unable to explain that. That is the case. Yes, you are there. It is happening as you said, but they were unable to explain it with what? Enthalpy alone. They only knew about enthalpy. Now this is a plus delta H. No, this is endothermic, right? By using the enthalpy alone, they couldn't explain that because enthalpy wise reaction should not happen, but still a reaction is happening. Then they realize there's another thing they haven't understood is lying in existence at that time, and that later they figured it out. That is called what? That is called the unknown thing at that time was entropy. By understanding entropy, they were able to explain how even endothermic reactions are happening spontaneously. Right? Now, with the entropy in the picture, they were able to explain that also. That is why it is very important when we are learning about thermodynamics. We were learning about enthalpy first thing, and later they realized the timeline. Later they realized there was another thing. Enthalpy alone couldn't explain everything. They later figured it out. It was entropy. With the entropy and enthalpy together, they were able to tackle many of the questions, and they were able to make machines. Are you okay with it now so far? Just the opening, right? Right. Now that is why entropy is very good. Entropy is used to explain how both reactions can be explained. How? By combining with enthalpy, how these reactions are happening spontaneously, how some reactions are not happening spontaneously. Very good. Yes. That is the purpose, that is the usage of entropy. Now still we haven't discussed what is entropy, right? One of the most interesting parts. Now listen carefully, right? Now entropy. Right. Entropy is like this. It's like a universe. Okay, I'm asking a question. Have you ever thought why water is falling down in a stream? There's a direction, right? When you look at the universe, we feel like there's always a direction, specific direction. Water is falling down. Sun is what? Setting from a specific side. Why? Always. Huh? Yeah, it is gravity. Okay. Now, if I ask a question, why gravity is placed this way? Now, gravity is a law, right? Very good. Gravity is a law. These laws are means laws in the universe. Always our universe is following a certain set of rules, natural rules. We can't break it. We don't know how it was created, but somehow we know there's a certain set of rules. We call that physics. We can't bend physics, right? That is how our universe is created. Maybe in another universe, physics are functioning in a different way. But in our universe, this is how the physics works. We really don't know why it exists, who created it, but still we know it's there. There's a pattern, there's a law. That is called physics, right? Now remember, but still they understood there's a direction. Even in physics rules, there's a direction always happening. For example, let's say time. Time is always ticking forwards, right? Now, when you're looking at the universe, they understood something. I'm going to ask you if there's a tree under the tree, the leaves are falling down, right? Is it? Now, is it falling down? The next day when you get up and see, will you see a pile of leaf on one place? Or will you see all the leaves are scattered around? What would you see? Pile of leaves on top of each other, neat, ordered, or is it? I'm asking you. Just a normal fact question. What will happen most likely? What is more likely to happen? Scattered. Which one is more ordered? Is this one is more ordered or this one is more ordered? First one is ordered. This one is disordered, right? So universe not only over here. This is the pattern of the universe. Universe, that is how our universe is functioning. Universe is functioning always from ordered to disorder, right? Universe is always functioning from order to disorder. This is the direction of the universe, not in reverse. If you want to reverse it, what will happen? Someone needs to put some energy against it and put a pile of leaf on top of each other. But next day again, it will going to get scattered. To scatter, you don't need to put energy. To make something in order, you have to put some energy. Why? Because we are working opposing to the direction of the nature. Nature prefers disorderedness, right? Now I'll move on to next slide. Now we realize that as physicists, universe is expanding. Started at, we call it a big bang, right? It is universe it's expanding like this. For some reason, 13.6 billion years ago, universe started to happen. We don't know the reason. It started off at a one small tiny teeny dot, even smaller than the head of a needle. Whole universe started like this. Whole universe, you can imagine. All the masses in one place. Now we call it as singularity, right? You don't write this in exam, singularity. One place. From that point onwards, it is starting to expanding and expanding, still expanding, right? It is expanding. Our universe is expanding, expanding and expanding, and one day it will stop expanding and it will freeze. Now we here at the right in the middle. Still the universe is expanding. Now at the beginning, universe in ordered, right? So it was in order. And now in this direction, at time zero, clock started to tick at time zero. At time zero, at the beginning of the universe, maybe we don't know someone has created or we don't know the reason still. And we know in time infinity, after billions of years past, it will freeze. It will stop expanding, right? It is in order at the beginning, very ordered. And one day it will stop expanding. Now remember, scientists realized when the things are in order, it has less entropy. So therefore, if you take about the entropy of the universe at the beginning, entropy is zero. And one day it will reach entropy infinity, maximum value. Entropy infinity. At that moment, universe will stop expanding. Right? Now we are in the middle of this journey of universe from order to disorder. Now we are right over here. Right? We are right over here. One day it will stop expanding. Stop expanding and everything will get free frozen. Time zero to time infinity. This is a timeline. I did you understand something out of this? Right. Okay. That's okay. That's okay. Right. Now remember. Now I told you entropy is at zero. Entropy is at the maximum level infinity. Right. Now remember when you go down the timeline, entropy is increasing. Right. Is it understood? Little by little, entropy is increasing. Before that, you should understand what entropy is. Now I'm trying to explain you what entropy is. Right. Right. Now the entropy is moving. Right. Entropy means the universe is becoming disordered. Disorder is increasing. Entropy increasing means disorder increasing. Okay. Wait. I'm coming on that point. If I tell you what entropy means, you will not understand it. If I tell you a definition, you will not understand, right? Because entropy means a very profound theory. Now, if you're following me through, you'll understand what entropy is law after that, right? Okay, right. Now, disorder is increasing, order to disorder, right? That clock is ticking. Now, I'm asking you this question: what is time? What is time? You don't know. I'm going to tell you this thing. I'm going to keep you in a room, a closed room, no windows, inside there. You can't see outside. You are in complete darkness. Will you be able to tell the time? No. Why is that? You are in the darkness. You can't see anything outside, right? No window. Let's say you are not in the darkness. You have the light here. Still, can you see? Tell. No, nothing. You can't hear anything. Sun is not there. No sun is there. You can't, right? You can't tell, right? Now I'm going to put a window here. Now will you be able to tell now? Yes. Why is that? Because time means you are telling the time based on a change. When you look outside, you can tell in outside change is happening. Change is happening. So time means change. Change in the universe. Right? Now the change in the universe means universe is changing from what? Order to disorder. Order to disorder. That is the change. Right? So this change, the rate of change is actually called time. That is called time. That is why I told you one day the clock will stop clicking. Why? Entropy will not change anymore. It's at the maximum level. There won't be any change. So therefore, at that time, time will be frozen. Time frozen. There will be no time. Right? Everything is frozen. Right. Now let's move on to that. Now the thing is, uh, now we are coming on to that little by little. Uh, put the heading as chaos in the universe. Now it is called chaos in the universe. Now otherwise, if I didn't tell you the background, you will be wondering what is chaos in the universe. Now what do you mean by chaos in universe? In the universe. In the school they tell you chaos in the universe, you will be get like wondering what that term is. What is chaos? Yeah, chaos means disorder in the universe. That is what we discussed now. Chaos means the disorder, scattering, disorder, disorder in the universe, right? Now you can understand, right? You can connect it. The expansion of the universe, falling on the falling leaves and scattered. That is why we call chaos in the universe. You can watch a YouTube. That's the theory called chaos theory. This is actually the second law of thermodynamics. First law is energy cannot be created. Now we are talking about the chaos in the universe with the now we are talking about the second law of entropy, second law of thermodynamics, right? Chaos in the universe. It is called chaos theory, right? So you can watch a YouTube video and you can understand it much further, right? Okay. So don't write about the falling leaves, entropy zero to infinity. Don't write at the exam. That is only for your only for your profound understanding, right? Otherwise, you will get like it's a very interesting topic. That is why. Okay, right. Right. Let's try the definition now. Right. Entropy is given as S. The entropy we call S. Right. The entropy Yes, yes, definition, right? Not that blah 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 stuff, right? Now we are at the part that is required in exam. Did you understand what I was telling you previously? Okay, that is only the introduction, right? The movie intro, right? Now what you are writing, everything we are discussing now, it is needed for exam. Right? It will be a walk in the park now. If you can understand the previous thing, this is just walk in the park. Otherwise, I could have just given you the note, but I want you to understand the theory first, right? Not to just to memorize some little words. Right? The entropy is of a given system. Entropy means uh, the number of definition, the number of possible arrangements, possible arrangements, number of possible, underline this, possible arrangements of particles, the number of possible arrangements of particles and their energy in a given system, in a given system. The number of possible arrangement of particles and their energy in a given system. Now, how do we relate this to our thing, right? The number of possible arrangements of particles and the energy in a given system. Now, right? For example, when the same number of leaves are in a pile like this, and the same number of leaves are scattered on the ground, which one of these are having? This is the ordered. This is the disordered, right? Now, which one of these scenario can have more arrangement of particles? Arrangement means this part, this disorder. You can have multiple arrangements, right? Here you have only very fixed number of arrangements, right? And they have understood, right? When it is disordered, you can have multiple number of arrangements. More number of arrangement means it has more entropy, right? More number of arrangements can have more number of arrangements. Number of arrangement means it has more entropy, more S. Now with this scenario, you have only less number of particles are closer to each other, so therefore you can have only limited number of arrangements. Here you have less number of arrangements, right? Same number of particles plus less number of arrangements. Why? Particles are near each other, so you can call less entropy. Less entropy. Less entropy. What is entropy means? Number of number of arrangements, right? So it means more number of arrangements, no? So it has more entropy in a disordered system. In an ordered system, you have only less number of arrangements. So you have only less entropy. Okay. Now you have a system of, let's say, solid. You have solid. Let's say a solid of, okay, bromine liquid. I am converting into bromine gas, which has high entropy, which state is having high entropy, which state is having less entropy. Which state is having higher entropy? Br. Why? Many different arrangements can be there. There's more space, right? So that is me. So universe always prefers what? Low entropy to high entropy. Universe is always, you can call it, you can give different definitions to some god or whatever it is. I don't know. So they prefer less entropy to high entropy. Less to high entropy. Always universe favors high entropy, right? Less entropy to high entropy. Okay, right. But remember, now if something is moving from less entropy to high entropy, the reaction is favorable. You may call it okay. Now is this reaction spontaneous? Yeah, you can tell spontaneous, but be very careful. With only entropy alone, you can't explain it. You have to combine entropy with enthalpy. You have to combine. By combining them, later we are learning something called, the combined thing is called Gibbs free energy. Later next we are learning that Gibbs free energy. By looking at Gibbs free energy only, you can tell whether it is spontaneous or not. Yes. By looking at the entropy, it is spontaneous. But with that only, we can't explain that. We have to combine entropy and enthalpy together and getting a value called Gibbs free energy. Is it clear now? So be very careful when you are commenting on something, a reaction. They will ask you whether it is spontaneous or not. You tell okay. Entropy wise, it is highly likely. But you can't completely rely on entropy only. You have to combine entropy and enthalpy together. Just the reaction is, whether the reaction is, let's say it is exothermic, still you can't tell it is spontaneous. Why? You have to think about entropy also. Entropy and enthalpy together combined only you can comment on the spontaneous of the reaction. Is it clear now? Right. Okay. Now you understood the whole thing actually. Okay. Okay. Right. Uh, Now I'm going to give you an reaction. You should, in 3 lines, with your knowledge on entropy, this is a decomposition reaction. In 3 lines, using your entropy knowledge, whether this reaction is spontaneous or not. Explain in 3 lines. By you can that is be careful now. Look at it. Ah, look at the states, reactants and not spontaneous. Why? So not in high entropy, right? It has high entropy. Now here there's no gas, no. Only one solid there. There's a solid and gas. Which side would you prefer entropy wise? Right. Yes. So entropy wise reaction is feasible. Remember, keep that in mind. Entropy wise. Right? It's right in 3 lines. Comment on whether this one is having high entropy or less entropy. Uh, Comment on that. Now, with the last 3 lines, explain. Short and sweet, 3 lines. Now they are asking that exam, huh? This one is in gaseous state, it has more entropy. There's more free space, right? More entropy. This is more ordered, this is less entropy. Your whole package is having, compared to the products, less entropy. All right. Okay. Now for homework, you should tell entropy wise, right? Only by looking at the entropy, nothing else. Still, we don't have much knowledge to tell whether it is spontaneous or not thermodynamically, or thermodynamically feasible or not. Entropy wise, comment on this. For homework, which side is more preferred? Easy, right? Very good. And I'm going to end the class for today. Take care. Bye bye. Okay, you're welcome. Okay. Okay. Okay, thank you. Bye bye.